I got another gadget to show you guys today. This is another fancy meter with function generator and an oscilloscope all built into one handheld unit. Dual trace scope, 50 megahertz display. We're going to put this thing through its paces and see how it looks and how it performs. Actually, it's not bad, but it is a DSO. All right, today I have another gadget to look at. This is an oscilloscope. Actually, it's quite big. I don't even know what brand. It's called a BSIDE 09 oscilloscope graphic multimeter. Powered by two 18650 lithium batteries. Dual channel oscilloscope, but it's in Chinese, so I can't really read it. But we'll figure this out. Oh, it comes with a carry case. Cool. Okay. So what do we got in here? Let's see what this is. Well, there is the scope itself. It's called a BSIDE. BSIDE 09. It's got an output on here. What is this? Oh, it's for testing and your charging port. USB-C charging. Comes with probes, or a probe, and clips. Actually comes with two probes. Probably the best part of this is the probe. Who knows? We'll find out pretty quick once I get to testing the unit. And of course, a charging port. Don't know whether it's got any charge in it or not. I would imagine it's probably got some part of a charge. Let's turn it on and see. Nice display. Nice display. It doesn't have a stand, does it? To stand it up? Is that a stand? That's probably for fuses. Battery's fully charged. Well, let's check it out. Let's see how this thing works as a multimeter. First of all, we'll test it some AC and some DC voltages. What is this port on the bottom for? Is that for current measurement? 2000 amps maximum. What? 2000 amps? I don't think so. It's got two current ports. One's a 200 milliamp and the other one says 2000 amps. Well, maybe. Okay, we'll plug our probes in here and we'll do some measurements first of all. So right now it's on, let's say, DC. Well, it even tells me when I plug probes in what I'm plugging into. Or is it just flashing for a reason? Is this a touchscreen? No, probably not. Mode, menu. Might help if I read the instructions. English, hope it's in English. Auto off. Backlight's at 100%. Backlight time 120 seconds. That changes the language, you see, between English and Chinese. Mode, okay, there's the. That would be for the signal generator, I guess, is what that's for. And then the oscilloscope. And then meter. Okay, well, what happens if I put these probes onto something that's got some power on it? Let's just see what happens. It's in DC mode right now. I'll turn on my power supply. It's set for 12.2 volts. And we'll just... nice probes. We'll clip this on here and... 12.226. That's probably right on the money. Let's just compare it to the benchmark standard here. The good old fluke. It'll be a fluke if it's accurate. 12.25. This one says 12.221. That's pretty close. Turn this up to 19.3, 31.2, 31.1, 32.1. I'm just dialing down my meter. 11.0. $13.8. Yep, it's accurate for DC voltage. Let's check it for AC voltage. I just so happen that I've got AC power right here, so we'll just plug it into AC power. Will it automatically switch to AC, or do I have to switch it manually? Looks like I have to switch it manually. How do I do that? Ah, that switches between DC and AC right there. It also switches a true RMS or DC. So in AC mode, and it tells me which probes to use. You see it's flashing. If I stick my meter in here, $119.72, that's mains. Let's see how my variac is set. Down at 112. See, it must have got bumped. Normally I keep it at 120. Yeah, it lights up in red to let you know the voltage is high. What happens? Where does it go back to white? Let's see. There's the threshold there. 89 volts, and we hit 90 volts, and it goes to red. And it flashes. It flashes a bar on the top of the screen. Actually, it flashes a bar on the top and the bottom. Here you see it flashing red to warn you that the voltage is high. If I dial it back down, that red goes away. My variac can go up as high as 150. Okay, so that's AC voltage and DC voltage. Press down the auto peak button. Right now it's showing RMS voltage. If I press down the peak button, it's now going to measure the peak to peak voltage, which is 167.09. That's what the actual waveform peak is, 167 volts. The average being 118. Go back to regular measurements. Okay, we're at 119.4. I'm just kind of going through the operation now. So this selects AC and DC. And if I use the right or left arrow, it will then switch it to, this is to ohms, and a diode test, I guess, as well. So, right, 0 ohms. We'll just measure some things that I've got kicking around here on the bench. 200 ohm resistor sitting here. Let's measure that. Measuring kilo ohms. So it tells you right here what the measurement is. So you see it's measuring in kilo ohms. So it's 0.2 kilo ohms or 200 ohms. I'm going to put this up alongside of my fluke meter just so we can check it for accuracy. And these resistors are probably way out of spec. Some of them will be anyway. This resistor here is, well, it's supposed, well, my meter's probably not accurate anyway. My probes are 1.6 ohms, so add 1.6 ohms to this reading. This should be a 1 ohm resistor. And measuring 2.4, so pretty close. That's just the fluke meter. The probes themselves have some resistance. So it's not that accurate for I could probably use my low ohms meter and get a more accurate reading. But what does this one say that this 1 ohm resistor is? 1.4. What do the probes show? The probes show 0.1. That's this goes into a display out on it after a few minutes just to save the battery. Let's measure this resistor here. This one's measuring 478 K. The display's reading in mega ohm range, so 0.477 meg, which is 477 K. It's a 470 K resistor. How does this one measure up? Looking pretty damn close. Let's look at this one. Let's see how far off this resistor is. So this one is measuring 51K. It's 49. That's gray. It looked like purple, but it's not. It's gray. So 49000, 449K. It's measuring 51. It's a what 10% tolerance resistor, so that's probably within spec. It's a carbon resistor, right? 51K. How does it measure up on the Fluke? The Fluke says it's 52K. This is an 8 ohm resistor, 50 watt. I use this for loading down amplifiers when I want to make smoke. This will switch into ohms mode, 8.1 ohms. The Fluke is going to measure a little bit higher because the resistance of the wires, so we're measuring at 9.5. Remember 1.5 or 1.6 or 1.6 for the wire. So it's accurate. What else can we measure on here? We can measure capacitors as well. So let me put this into capacitor test. We'll measure a couple small caps and then a couple larger caps, or one small cap, because that's all I've got hanging out here is one small little cap here. So I felt like digging out. So this is a 0.002 microfarad, which is what it is, a 0.002. Capacitance testing. .6 nanofarads, which is 0.002 microfarads. This measures in nanofarads, as you can see right there. So, capacitance measurement is good. This one's 330 microfarads. Fluke goes first. 330 microfarads. So 329, 328.9. It's close. It's close enough. Close enough. Try a 1000, as that's just the next one I've got handy here. Short it out and drain it completely. This is the 1000 at 10 volts. It's gone into MF with the big F, right? Not microfarad, so 1006 or 1069, 1.06 anyway. And we'll do the same on this one here and see what this one will measure in microfarads. 1056. So we're getting the same type of reading. This time I'll measure an NPN transistor. It's an NPN, so positive on the base. Fluke meter. We have a 0.531 drop, and so this transistor is good, as you can see. Base to collector, 0.52, and 0.53 base to emitter. Over to this one, and we'll select diode test, which is back in this mode. Where is it here? Back in that mode there. Oh yeah, it's in resistor mode here. You see, it tells you here your resistor mode, capacitor mode, and voltage mode. When we're in this mode here, we have to switch it. So using the up and down keys, switch it to diode, switch it to continuity. Continuity is just for a beeper, so it beeps immediately. So we're going to switch it to diode test, and then put the meter on. 0.5 and 0.54. Right. If I reverse the probes, it should say overload, which it does. Oh well. Right, and we'll check for shorts, and we're good. Base to collector, or base to emitter, base to collector. No beep on this, like the Fluke. The nice thing about the Fluke meter was it gives you a beep. It gives you a single beep if it's good. right, like that. And if you've got a short, you do that, right? So that's the nice thing about the flukes is the little beep. But this one here, you get a look at the meter. All right, so we've tested diodes, we've tested capacitor, we've tested resistors, we've tested voltage. And I haven't tested current, but I can only do milliamps. We're going to do a little simple current test here. I have a 200 ohm resistor. We have 12 volts. Look on the fluke meter, 12 volts, right? We should see 60 milliamps, because Ohm's law says that 12 volts through a 200 ohm load should be 60 milliamps. So there's our voltage. I only have two hands, 12 volts, and I put the meter probe on to here, and we see that we actually have 59.8 milliamps. That's pretty damn close. Let's be 60 milliamps. 60 milliamps for 12 volts through a 200 ohm load. So current measurement is spot on. Okay, next we will move on to the function generator. This is the function generator here. We can generate different signals, and that's of course out the output port here. So it's telling me now it's going to do a sawtooth and just cycling through the different full wave, half wave, triangle wave,
square wave,
sine wave, and then back and then to a DC voltage. We'll look at the output of this on my analog scope so that we can see what the output looks like. And it's set for a 3 volt output, and then I can hit the frequency here so I can dial the frequency up and down. Right, so it's at 1 kilohertz right now. I can change it to hertz or kilohertz or megahertz. Set it for 2 volts peak to peak sine wave. Let's take a look at the other scopes. As you can see, it's a beautiful sine wave. Exactly what I would expect it to be. 2 volts peak to peak. We're looking at 1 volt per division on my ×1 probe. We're seeing exactly 2 volts peak to peak on the scope. I will also show it to you on the Uni-T. Both scopes are in agreement. I'm now going to turn the voltage up. We're going to go to 2.1, 2.2. We're going to take it up to its full, measuring it at 3 volts and see whether we're getting 3 volts. It looks to be about 1.5 per division, so that's a total of 3 volts. Let's check it out also on the Tektronix. Once again, they're claiming 3 volts output, and that looks like 3 volts output. So this is a sine wave we're looking at now. The next one's just a DC voltage. And now we're looking at a sawtooth. Sawtooth is also set to 3 volts, and as you can see, we have a nice sawtooth signal here. I'll just drop back my sweep a little bit. And it's a sawtooth signal. We're not seeing the line coming down because it is so fast. It's not really showing up on camera, but it is there. As you see on the digital scope, it's fast enough to catch that. The analog scope, it's there. If I turn out the lights, you'll see it. It is there. It's just that that switch is happening so fast that the beam doesn't even get a chance to draw it. It's happening so fast. Next is the full wave, 3 volts. Peak to peak, and the next is a half wave, again 3 volts peak to peak. This one's a triangle wave, looking good, and of course a square wave. Again, the switch point is so fast that on the analog scope, unless I shield it, you can't see it, but on the other scope it's clearly visible as a square wave. And then back to a sine wave. We're going to crank the frequency up now and just see how it responds at higher frequencies. If we note the frequency readout here, this is 10 kilohertz. It's measuring 10.13 kilohertz. See, I'm just going to adjust my time base here. 90 kilohertz. It's going to go to 100 kilohertz. We'll just keep going. That's 900. Okay, we're at 1 megahertz now. Let's start going up and just watching what happens as I go up through the frequency. You'll notice over 1 megahertz the voltage is starting to drop. 5 megahertz. Waveform's still looking pretty good on both scopes. 5 megahertz is the limit. Next we're going to go into the oscilloscope mode, which is the more interesting of them, because I want to see how well this displays incoming signals. Got a couple probes with it. We'll use the probes that came with it. We're going to try it on complex video signals and so forth as well and see how it handles that. Okay, what I'm looking at here is I'm looking at color bars from my camera. And this is there's the color burst. It's not locking in that well. Again, it's a digital scope. I don't expect that it's going to lock in very well to video signals. My Uni-T certainly doesn't do any better. This is a 50 megahertz bandwidth scope. My Uni-T is 100, and looking at video signals, it doesn't look any better than that. I can show it to you as well. As you can see, the Uni-T really doesn't do much different. It looks about the same. Okay, so that's looking at one line. That's a line we're looking at, not a field. That's one line. If I dial it down, we can look at fields. This is that's a video field. That's a full vertical field. I'm not synced up on it there, but that's a vertical field. This is a horizontal field. That's one line of video. That's two. That's almost 2.5 lines. But that's what you expect to see when you're looking at video. You expect to see a nice, clean waveform. And if I were to actually display video on there, which I could, it'll display beautifully on a proper scope like this. So this is real world video that you would look at on an analog scope, and this is where these digital scopes just don't cut the mustard. There's video on an analog scope. I'll show you the digital. Yeah, that's we're looking at black right now. Video has ended. Wait for the next. Okay, so now we're looking at video. And as you can see, video, just you can't make anything out on here. Using one of these to try to service the video circuits on, say, an analog television, it's just not going to work. That's simple as that. Basic waveforms, audio waveforms and stuff, and signals from electronic circuits that are generating digital signals and waveforms, yes. Complex waveforms like the I pattern off of a CD player or video, these scopes just don't work. And my Uni-T is exactly the same. It is completely useless. That's why I have an analog scope. Audio signals, for example, are fine, and you can save them with using the run stop button. You can capture an analog signal. You can capture an analog audio signal or anything. But looking at audio signals are fine. And I'm just changing the voltage here, 50 millivolts, 100 millivolts, to go up to 5 volt input, and then with your 10 volt input, I guess, yeah, 10 volt division, and then with your 10 times probe, you can have 400 volts maximum with your 10 times probe. 50 megahertz bandwidth. We are right now on times 1 probe. So we're looking at 100 millivolts per division here, which is about what I'm seeing. I think there's a half volt output on this media player that's playing. 2 channels. You can turn the second channel on and off here. Switch to the second channel. Oops. Menu. Channel 1 enable. Channel 2. You can enable channel 2. Then you've got the dual traces. Coupling. AC and DC, all times 1 probe. There we go. Channel 1 times 1 or times 10, you see. You can change your coupling between channel 1 and channel 2, AC or DC coupling. Turn it on or off so you can have a single or dual channel scope. I've just got it set for single channel mode. 2 probes go in the top, and that's the output for the function generator. And on the side here, you've got calibration ports and the charge port. So for calibrating your scope, you clip your scope probe on, ground. And this would be a 1 kilohertz square wave output, like most of them. There it is. And then we can calibrate this. I'll just turn down the gain. Now we're measuring the internal generator. What this is useful for is if you've got to calibrate, there's typically some calibration adjustments here for the times 10 probe. When you put it in times 10 mode, you adjust to get away from this slope. So there's a slope there. There should be a calibration tool in the bag here somewhere. At least they usually come with a calibration tool. There we go. That's better. That's what we want. The tuning tool they gave me wouldn't fit. That's what we want to adjust. We want to adjust that so that that is completely flush, like that. That's what you do to adjust them. Of course, you guys probably want to see what's inside this thing. I don't know if I can get it out of this rubber. I should be able to slide it out of this rubber case. It doesn't look nearly as nice when it's apart. Phillips screws. Where's my small #1 Phillips? We'll just pop the screws out and pull the back off this unit so you guys can see what's in it. Oh, okay. And there it is. Popped apart. Not too bad. It's got two 650 batteries in it, as you can see. A couple fuses in here for overcurrent protection when you're testing it with the current measurement. Does have one on the, looks like it's got one on the main high current probe as well. There is a fuse there. That's for if someone is dumb enough just to plug a probe in there and not have the proper current. I don't know that it'll measure anything without it, but maybe it will. Maybe it'll measure a few amps. But we'll see what the amperage of this fuse is. Just for the hell of it. What is it? This is a impossible to see number. We'll get the eyeballs on it and check that out. 10 amp. 0.2 amps, 200 milliamp. That's the low current fuse, that one. Anyway, that's the unit itself. It's a single board solution. I don't think there's probably much to see on the other side. And all your measurement is done right down here. Yeah, as I thought, there's really nothing to see on this side. Just the display, the buttons. Oh yeah, there is some more stuff down here. That's probably the scope measurement equipment right down there. That's the scope measuring. And the IC, they have etched the top off. So you can't see what IC they were using. They're protecting their secrets, and I'm sure there's some other stuff under the shield here. I'm not going to remove it. It's used to be soldered down to the board, so I'm not going to remove the shield because then it definitely won't work. But there's the chip that measures everything for the scope portion, and as you can see, they've etched off the top. They've laser etched it. It's actually etched right down, or they've milled it off. But there's a groove here, so they've milled this down. So there's no way of knowing what that chip is, which says that this is probably a pretty common chip that they're using, and they don't want someone copying the circuit. So they're just kind of trying to keep their secrets secret. Or they've stolen somebody else's. Generally it means it's a pretty common chip. Alright, I'm going to throw this one back together. It might take me a while to get this back into its protective red cover. Good as new. I should have taken that plastic cover off while I was in here. There's a protective film on here. Probably should have taken that off. It may have made the display look better when I was filming it. Oh well. All done. This one's back together. It's no worse for wear. Looks to be a pretty nice little meter, and it's got your basic oscilloscope functions. So if you're looking for a basic scope that will do all your basic functions other than looking at things like video, and I'm sure the eye pattern from CD players would also be problematic. Good batteries in it. Those should last for a good long time when it's operating. to 18650s. I like the display. I like the multi-digit display with 4 digits of resolution to the right of the decimal point, 5 digits total. I like that, and accuracy-wise, it seems to be pretty good. So this one's going to be sitting on my bench somewhere. I'm sure at some point I will be using this from time to time as a secondary meter. But for now, I'll say thanks for watching. I'll put the link in the description. Came from Banggood. We'll catch you in the next one. Bye.